Hello and welcome to another slide video from the Cornish Radio Amateur Club, and today this video is in the Foundation series, that is leading to the RSGB Foundation certificate, the exam, which in turn leads to the issuance of a Foundation license by Ofcom. And today we'll be looking at transmitters. Now, you should all have a copy of Foundation now if you intend to take the exam, and you'll notice that transmitters are covered on just one page in Foundation now. So this slide video may well be over the top for you, and there is an alternative learning strategy, and that is just to read and learn the facts on that page and check with the syllabus that you've covered everything you need to know. However, you may wish to get a little bit of further background on transmitters, and in which case this video is for you. So this video goes into more detail than you absolutely need to learn for the exam, so you should think of using it for background and general understanding, and not fret too much if some of the concepts are a bit complicated. Right, without further ado, let's have a look at the syllabus. The syllabus, 4A in the syllabus says the simple block or concept diagrams of the transmitters. See Table 2, and we'll be looking at that in a minute. 4A1 says identify the items in a simple transmitter block diagram and recall their order of interconnection. Microphone, audio, brackets microphone, amplifier stage, frequency generation stage, modulator stage, RF power amplifier stage, feeder and antenna. Right, let's have a look at that in the syllabus. That's what the syllabus then looks like. And it says on the left hand side, the block or concept diagram shown will be used for all assessment questions. It is not intended that the blocks will relate to any particular architecture of radio, merely the basic functions that need to be performed. Hence the title concept diagram. The symbols for the microphone antenna should also be known, and you will recall that the microphone there on the left and the antenna on the right are two of the 10 symbols that you need to learn for the Foundation exam. And so any questions relating to transmitters in the examination will use exactly that diagram with 1, 2, 4 and 3. Although the labelling may not be the same, the position and the interconnection of those blocks is something you need to be able to understand. Now, when they say a block or concept diagram, what they're saying is that if you go and buy a transceiver or transmitter off the shelf, it may well not be exactly as per these blocks. If you dig into the guts of it, it may do things using a different architecture. There's more than one way to skin a cat, but if you think about this concept diagram, you're pretty well going to understand basically how a transmitter works and what it's trying to achieve. So let's have a quick look then at the block diagram, and there it is, and we'll replace the numbers with labels there to make it a bit simpler to understand. So on the left you have a microphone, and on the right you have an antenna. And we'll go in and dig into each one of these blocks a little bit to understand what the function of the block is. Again, you don't have to necessarily understand to this level of detail, but it may be helpful. Let's first look at the audio stage. Now, when the guy on the left speaks, he sends out sound pressure waves, and they vibrate the microphone diaphragm, and that in turn produces a small electrical signal which is sent to the audio stage, and it's something like this. There you can see the longitudinal compressions of the air as he speaks. That rattles the diaphragm, and the diaphragm moves a little coil in a magnetic field, and it produces a signal which is a facsimile of what he has said, the vibrations that he has created. Now that signal is very, very small. It is an AC waveform of the audio frequency. It's an alternating current waveform of the audio frequencies. But it may also contain background noise and bangs, etc. And that will mean that the frequencies in that waveform will exceed desirable speech frequencies of between 300 and 3000 Hertz, or 300 to 3 kilohertz. You'll remember that when you are learning about frequency ranges for the foundation examination, one of the things that you learn is that normal hearing is between, I think, 100 and 15 kilohertz, 100 hertz and 15 kilohertz, but that the desirable speech range of frequencies that we send to air is between 300 and 3000 hertz, and that if we limit the frequencies that we send to air, or we transmit, to that range, then normal speech is entirely intelligible, but it's not consuming too much RF bandwidth unnecessarily. So if you bang the table, you will find that that is a complex waveform, and it contains all sorts of frequencies. Many of them will be above 3000 Hertz, and so we need to make some efforts to limit the bandwidth. Also, as I mentioned, the signal at this point is very low. So the first thing that is put in is an amplifier, and it's written there on the screen, amp, and shown by its symbol, which you don't need to know, which is a sort of triangle. And there is a mic gain control there in yellow. And after the amp is a filter, a bandpass filter. Again, the symbol you do not need to know, but that limits the frequencies, as discussed, to between 300 and 3000 Hertz. And so coming out of that filter, going to the next stage, which is the modulator, are audio frequencies, AF. So, reiterating, the amplifier boosts the signal from the microphone. And there we have the boosted signal. You can see the amplitude, the distance from the peaks at the top to the peaks at the bottom, is greater than the signal from the microphone by a small amount, because as depicted, we've turned down the mic gain. And then the filter limits the bandwidth to between 300 Hertz and 3 kilohertz. Then out of the filter, in red, we've got a signal. It's about the same amplitude as after the amplifier. It may have lost a little bit going through the filter, but it's about the same amplitude, but the frequencies now are limited to between 300 and 3000 Hertz. Now if we turn up the gain, by rotating the yellow knob, then the amplitude of our signals is increased, because the small signal going into the amp has now become a larger signal coming out of the amp in the audio stage. Now if we turned that too far, we would be feeding too much signal to the modulator. And we will be looking at the effects of over-modulating later on in this video. So that switch, that knob rather, or the mic gain, needs to be set at an appropriate level so that we correctly modulate our signal. As I say, we'll be looking at that later. Also, going into the modulator, we have an oscillator. And there you can see it's producing the RF frequency. So, in our concept transmitter, if we were transmitting on 7.1 megahertz, the frequency there going into the modulator, as shown by the white waveform, would be 7.1 megahertz. Along the bottom, I've shown the amateur band and another band, an adjacent band. And if you look at the carrier there as depicted by the vertical arrow, then that might be 7.1 megahertz, for example. So the frequency then from the oscillator, to repeat it, it's the final RF frequency, and we've shown it in the frequency domain, that is, looking at it rather than in the time domain, which is the squiggles. We're looking at it, if you like, a map of where it is on the bands, with frequency going off to the right. We've shown it as a vertical line, and it's correctly within the amateur band. Now, the oscillator might not necessarily be a variable oscillator. It could be a crystal oscillator, and therefore would have a fixed frequency. It could also be a variable oscillator. And if we turn the knob on the variable oscillator, which we're going to do now, then the frequency changes. You can see that the final RF frequency, the wavelength has increased so that the frequency has gone down, and we've dialed our oscillator out of the amateur bands into another band, which is a bad thing. So we're now transmitting out of band. And this speaks to one of the syllabus items, which, to paraphrase it, says something like, be aware that incorrect setting of the oscillator may cause you to transmit out of band or to interfere with other users. And we'll have a look at the syllabus item later on to get the exact wording, but that's roughly what they're saying. So if we were in this position, we would rotate the knob then to the right like this, and we would increase the frequency so that we were comfortably back into the amateur band. Let's have a look at the function of the modulator. The modulator superimposes our audio signal, that's the AF coming in from the left, onto the RF coming into the bottom, and produces a composite signal. In other words, it overlays the AF on the RF so that when it's sent out to air, it can be received by somebody, and the AF can be removed from the RF, and that's how we transmit our voice signal from one person to another. So the AF comes in from the left, that's an audio frequency, low frequency signal between 300 and 3000 Hertz. That's mixed up in the modulator with the RF signal coming in from the oscillator, let's say 7.1 megahertz. And then the composite signal is sent off to the RF amplifier on the right. And the function of the RF amplifier is to take the relatively small signal, labelled modulated RF, okay, and turn it into a higher signal, which is sent up the feeder to the antenna, which is modulated RF at high power. At least that's what I've called it on this graphic. So take a moment to look at the various stages. Recall that the sound waves vibrate the diaphragm of the microphone. A small signal is produced in the audio stage, fed to the audio stage. It's then amplified and filtered so that we only have the audio frequencies of between 300 and 3000 Hertz. And that is sent to the modulator, where it is mixed with the final frequency, the final RF frequency, which is a sine wave in shape, and that is produced by our oscillator. The oscillator may be a variable frequency oscillator with a dial on it, and we need to set that dial correctly so that we are both in band, in the amateur band, and not interfering with other users. Out of the modulator, the composite signal, which is the combination of the audio frequency and the RF frequency, we call it the modulated radio frequency, is sent to an amplifier to boost it up, where it goes through a feeder to an antenna and then out to air. Let's have a look at the RF amplifier, feeder and antenna in a bit more detail now. Here at the RF amplifier, the green circle is meant to indicate the output power. Now the power is sent down the feeder and to the antenna where it is radiated, and that happens with a good antenna match. That means that the antenna is the correct length and the correct impedance for the amplifier, and if the two match, then we get a good result, with most of the power that comes out of the RF amplifier radiated into space for subsequent reception by another radio amateur. If we have a poor antenna, then the signal goes out but is reflected back at a point of mismatch and then causes heat to be dissipated in the RF amplifier. And that is a bad thing, and it can damage the RF amplifier. So the pertinent points here are that the antenna needs to match the amplifier or the frequency. So we need to have an antenna specific to a particular frequency, and that provided that we have a good match, most of the power should be radiated into space. But if we have a bad match, then the power is reflected back from the point of mismatch and causes heat and potentially damage to the RF amplifier. Now going back to the concept diagram again, there we have it, the audio stage, the modulator, the RF amplifier and the oscillator. And we're showing there two of the most important controls, the microphone gain and the frequency control. And we've discussed the function of each of those. Let's have a little look at the modulator again. Now, the type of modulator, or rather the modulator, depends on the type of modulation. The way of superimposing the audio, the AF signal, on the RF signal from the oscillator and joining them together or mixing them up before sending them off to air, there are a number of ways of doing it. Let's have a look at this graphically. There is a sine wave representing an audio signal, and I'm showing this in time domain. Don't worry too much about this. It just means that I'm looking over time on how the signal goes up, goes down and goes up again in amplitude. There's the AF signal, a fairly low frequency, somewhere in the range of 300 to 3000 Hertz. If I have amplitude modulation, then that is the signal that will come out of the modulator. It is the RF signal, but it is changed in amplitude in sympathy with the AF signal. And you can see the shape of the AF signal then being imposed on the RF signal. If it wasn't, then the RF signal would be a straight band of high frequency oscillations. But you can see that the amplitude of the RF signal is made to change with the AF signal, and that is amplitude modulation. Another common modulation scheme is frequency modulation. And here we have frequency modulation. Here you can see that the RF signal is changed in frequency in sympathy with the AF signal. You can see on the left of the graph there, the peaks are all bunched up because there is a peak in the AF signal, whereas in the center they're spread out, so the frequency is lower. And then that is because there is a trough in the AF signal, and then on the right hand side they bunch up again because there is a peak in the AF signal. So let's go through that again. there's a peak on the AF signal, and on the amplitude modulation, then that corresponds with the peaks that you see there. So the yellow peak of the amplitude, the AF signal, corresponds with the large amplitude of the modulated signal, and the peak on the AF signal in red corresponds with the one below it in red. However, for frequency modulation, the peak then corresponds to a high frequency being sent out to air, slightly higher than the carrier. These shifts in frequency are shown as being quite large on the graphic, but in fact they're quite small compared with the carrier frequency. But we have to depict it on a graphic, so it's slightly exaggerated. And the red one there, those are the peaks. So you can see that the peaks of the AF signal correspond to peaks in amplitude for the amplitude modulation and peaks in frequency for the frequency modulation. Conversely, the trough of the AF signal corresponds to low amplitude being sent to air and low frequency being sent to air. Now, one of the things we need to understand for the exam is the effect of over-modulation. And we'll talk through the syllabus items at the end of this show, but this probably goes into it in too much detail, but let's have a look anyway. There's our AF signal. That's coming out of the microphone, being amplified and filtered by the AF stage. And mixed with the RF, it produces this amplitude modulated signal. And when it gets to the other end, the receiver's function is to demodulate it. In other words, return it back to an AF signal played out through a speaker, as you might expect. If we show the case for it being over-modulated, the mic gain in this case is up too high, and so it cuts off completely the signal to air too early. And so the demodulated signal is a bit scrappy and scraggly, as you see there, and that's distortion. And we can see it if we hold the two signals up against each other, the original AF signal and the demodulated signal. You can see now they are different, and that is really what the definition of distortion is. That will sound unpleasant to the ear. Let's have a look at FM modulation. There we have, in the time domain, the changing of frequency from a high, slightly higher than the carrier frequency at the left to slightly lower, and then back to slightly higher. And that would be in sympathy with the AF waveform applied to the FM modulator. If we look at it in the frequency domain, here we have an amateur band, and we could say then that the lower frequency might be just on the edge of the amateur band, and the higher frequency might be a bit further up. The carrier would be between the two, and then in sympathy with the AF signal applied, the carrier would move up and down in a frequency modulated way. And that's all fine, because during that exercise we remained within the amateur band. If we then go to FM over-deviation, now for FM sometimes we use the word deviation and sometimes modulation. So I'm just thrown in the word deviation this time, because the carrier deviates up and down in frequency from its center frequency. Now here we've got a greater spread of frequencies, and that's shown on the top signal. The lower part of it now goes into another band, and that could be another user band. It could be, for example, taxis or Coast Guard or something like that. So now, as we modulate the signal, it travels out of band. And now at this point, we are causing interference through other users or other bands. So the same scenario might apply if we were in the middle of the amateur band, but over-deviating, then we would be just interfering with other amateurs. Serious enough, but not too serious. However, it is serious if we move on to other bands, because we're then outside the terms of our license. So that's showing the FM signal, the top signal then being in the time domain, and the bottom signal being in the frequency domain. They're representing the same thing, but just looking at it in a different way. Let's do the same with AM modulation. There's the AF signal, there's the RF envelope that's produced, and there's the demodulated signal. And let's have a look at that then in the frequency domain. How would that look in the frequency domain? And one of the tools for looking at it in the frequency domain is a spectrum analyzer. And this is what it would look like in a spectrum analyzer in the screen as you looked at it. There would be the carrier in the center, and then two sidebands there. And because we're producing fairly pure tones on this upper depiction, not a complex waveform of speech, but a sine wave pure tone at say 1 kHz, we would see the two sidebands there. If we were producing, and so I should say the carrier in the center, the upper sideband, USB, and the lower sideband. Now, if we were producing a modulated waveform as a result of speech, it would be complex. It would have, instead of just two pure tones as shown before, it would be made up of a number of frequencies simultaneously, and so it would look something like that. Now, if we over-modulate it, as shown in the above at the top of the screen there, you can see the over-modulated signal and the demodulated signal. That will produce out-of-band signals, because it will produce things like intermodulation products, which we don't need to understand. But here, what's happened is that the sidebands have spread out further than we want, and then the area in red is out of band. So although our center frequency, our carrier, is in band, and if we looked at our transmitter, the dial would indicate we were in band, because our mic gain is up too high, we're over-modulating and we're producing signals out of band. Or if we were in the center of the amateur band, perhaps we might be interfering with other users, other amateur users. So we've covered AM and FM. We've looked at the way they are modulated. We have looked at the effect of over-modulation. Now we'll look at another type of modulation, Morse or CW. And Morse or CW is simply produced by switching the carrier on and off with a Morse key. At the other end, this carrier and absence of carrier is translated by the receiver into audio tones, dits and dars. So here, this representation is, if you like, instead of the audio frequency representation before, this is showing the letter R, didar, dit. So that's the modulating signal, and that is what is sent to air. And instead of having sort of blocks of frequency, I've shown them rounded off a little bit. This is good practice, as it stops something called key clicks, but we don't particularly need to know about that. Now, we don't also need to understand what the concept diagram is for Morse, but it might be something like that. The oscillator always transmitting a frequency of, let's say, 7.1 Hz, but not being fed to the RF amplifier. When the key is depressed, the signal goes out to the RF amplifier, and when the key is released, the signal stops. So this is a way of switching the carrier wave on and off to going to air. Now, one of the points to remember is that with the foundation license, you are not allowed to construct your own transmitters. That comes with later license levels. If you built a Morse transmitter, as shown there in the concept diagram, it would suffer from some disadvantages and potentially cause interference to other users, although it would probably work. It would be okay for a very low-powered one, but if you had a high-powered one, you might find that all sorts of spurious signals were produced. So that is really just a concept block diagram, not something that you would use as a template to build something. So we talked about the transmitter. Let's see how that joins in to becoming a transceiver. A transceiver is a transmitter-receiver. So there's the stages that we have to learn for our concept transmitter: the audio stage, the modulator, the RF amplifier, and the oscillator. And connected to those a microphone and an antenna. In the next video we'll be learning about the receiver, and there are the three blocks for the concept diagram of a receiver. Tuning, coming in from the right-hand side and going to the left. Tuning, that is picking up the desired radio signal from air, detecting it or demodulating it. Those two words are synonymous, detection and demodulation. And the audio frequency amplifier, boosting the signal going to a speaker. So there's a transmitter and receiver. And if we add some way of switching the antenna alternately between the receiver part and the transmitter part, then we will have our transceiver. And we could put that into a single box, and that's what we've got. So we could represent that signal box at the other end by just a single box, just a transceiver. In other words, get rid of all of the detail in the green box and just write the word transceiver, connect a microphone and a speaker to it, and that is our transceiver. And the normal operation of the transceiver would be to alternately transmit and receive using the press to talk button, which we haven't shown, but I think you're all familiar with. So the head on the left speaks, the sound waves travel to the diaphragm of the microphone, and that results in a modulated signal going to air. It comes out of the loudspeaker, it's detected and comes out of the loudspeaker on the right and is heard by the recipient. And that's all well and good. So that is for voice. But sometimes we wish to use data transmissions. In other words, send characters to and fro. So in this depiction then we have the left-hand transceiver set to transmitting. In other words, the push to talk is depressed, and the right-hand transceiver is receiving. In other words, the push to talk isn't depressed. And then after that part of the conversation, the roles will reverse. So that's manual control of the push to talk. If we look at those transceivers, we can also connect boxes to them called terminal node controllers. So we take off the microphone and the speaker, and instead we connect these boxes TNCs. And to the TNCs we connect PCs or dumb terminals, some way of depicting characters on the screen. So what's happening here then, going from left to right, is that the PC produces characters which are sent digitally to the TNC. The TNC converts these characters into tones and sends them to the transceiver for transmission. The transceiver on the right receives the tones, passes them to the TNCs, it sends translates those into digital characters, and it goes into the PC. The TNC also has control of the PTT, so that when there are characters ready to be sent, it keys the transmitter and sends them. Similarly, when there aren't, it moves into receive. So this is the basic setup for a transceiver with a TNC. And if we just look at one end, this is actually a graphic from the advanced course. So we're moving ahead of what we need to know. But there we have the PC on the left, the TNC, and the transceiver. In other words, the operator with a dumb terminal, a terminal network controller, and a transceiver. One of the risks with a TNC is that the audio gain, the amount of audio produced and sent to the transmitter, may be too high, and it's difficult to measure that without looking at the appropriate dials on the transceiver, in which case the danger is that you may over-modulate the transceiver. So that just about covers or over-covers transmitters. Let's go through the syllabus items and just check that we've learned all we need to know. So syllabus 1.4a says simple block or concept diagrams of transmitters. See table 2. They're referring there to table 2 in the syllabus, and you should be able to draw those 4 blocks, label them, and attach a microphone and an antenna. So that's for A1. Identify the items in a simple transmitter block diagram and recall their order of interconnection. So a question might be, for example, the modulator is connected to A, the antenna, B, the microphone, or C, the RF amplifier. So by being able to recall the blocks, you should be able to identify the correct one. So I'll go through that again. For A1, identify the items in a simple transmitter block diagram and recall their order of interconnection. And the order is the microphone connected to the microphone amplifier, or the audio amplifier stage, the frequency generation stage, also called the oscillator, the modulator stage, the RF power amplifier stage, feeder and antenna. So if you haven't got those on board, have a look at Foundation now or replay this video. Technical requirements of radio transmitters. What do we require them to do? Recall that the frequency generation stage, e.g. oscillator /S in a transmitter, defines a frequency on which the transmitter operates. Now they've used a plural, oscillators, here. Sometimes oscillators are used in combination to add frequencies together to make the final frequency. So that's something that's covered in greater detail in the intermediate and advanced courses, and we talk about mixing up the final frequency. But the key point here is that the oscillator in a transmitter defines the frequency on which the transmitter operates. Recall that incorrect setting of these stages can result in operation outside the emitter band and interference to other users. We looked at the effect of having too much mic gain and therefore over-deviating in amplitude modulation and frequency modulation, and we saw that we had out-of-band operation if we had too much mic gain. We also saw that if we adjust the VFO, the variable frequency oscillator, and we tweak the knob in either too high or too low, we only showed too low, but the same principle is effective if we go too high, that we can set the final RF frequency to be incorrect, in other words, outside of our band or interfering with an adjacent user. Recall that the audio or data signal is modulated onto the radio carrier in the modulation stage of the transmitter. So recall that the audio or data signal is modulated onto the radio frequency carrier in the modulation stage of the transmitter. So that is the business about the audio, if you like, being superimposed onto the carrier, or the carrier being changed in sympathy with the incoming audio. You can look at it in any number of ways. Now here they've said or data signal. If it were a data signal, then if you recall that the digital signal from the PC is passed to the TNC, which makes tones. So we still send audio to air, but it's in the form of tones which are recognized by the distant end TNC. Recall that modulation is by varying the amplitude or frequency of the carrier, resulting in AM or FM modulation modes. We looked at AM and we looked at FM. We looked at how the AF peak resulted in a peak in carrier for an AM signal and a peak in frequency for an FM signal. Recall that speech can be carried by AM, SSB or FM, and that data may be transmitted by means of a suitable audio tones generated in a radio modem or TNC, terminal node controller. So radio modem or terminal node controller are virtually synonymous in this context. Now what we did not cover is SSB. We did look at the concept that AM had an upper sideband and a lower sideband and a carrier. All of the information required to reconstruct the AF signal is contained in a single sideband. So, in some circumstances, we strip away the carrier and the unwanted sideband, doesn't matter which one really, and we send only one sideband to air. And then through some special techniques in the receiver at the other end, the audio signal is reconstructed. So recall that speech can be carried by AM, SSB or FM. So they've put AM/SSB because both of those are the same. SSB is simply AM with the carrier and one sideband stripped away. Or FM. So we talk about AM and SSB as being envelope modulated because that depiction in the time domain, which you can go back and have a look at then, is thought of as being the envelope as it changes in amplitude. And then at the bottom of the screen, 4b3, identify drawings of an RF carrier and amplitude modulated, frequency modulated, and CW radio signals. I'd urge you to have a look then at the depictions in Foundation Now and also the depictions in this video. Understand the terms carrier, that is the unmodulated RF signal that is sent to air. Audio waveform, that's the AF signal, which originates from the microphone and then is boosted by the audio stage. And modulated waveform, that is a combination, if you like, of the audio waveform and the carrier. Recall the power amplification of the radio signal is carried out in the final stage of the transmitter, brackets RF power amplifier. Well, we showed that block there, and we showed a fairly small signal coming out of the modulator. That is at the final frequency, and it contains or has the modulation on it. But if we connected the modulator directly to the antenna, we wouldn't get any range, because the amount of power at that point is fairly low. So we need something to boost it up, and that is the RF power amplifier. It performs much the same function as an amplifier in a hi-fi system. As much as the signal coming out of, let's say, the record deck is quite small, but contains all of the information needed to hear the music, but at too low a level. So we put an amplifier before the speaker. Well, similarly, out of the modulator is everything we need to send to air, but the level isn't high enough. So we send it to an RF power amplifier first, and then on to the antenna. 4b5. Recall that the RF power amplifier output must be connected to a correctly matched antenna to work properly, and that the use of the wrong antenna can result in damage to the transmitter. We showed the little green blob travelling out to a correctly matched antenna and going off to air. We also showed that being reflected from a point of mismatch and coming back down into the transmitter and causing damage. 4b6. Understand that excessive amplitude modulation causes distorted output and interference to adjacent channels. We saw in the frequency domain the carrier and the upper and lower sidebands, and we saw that if we turn the microphone gain up too much, we had excessive amplitude modulation, and that caused the sidebands to spread out beyond where they should. And that spreading out meant that it caused problems to adjacent channels, interference to adjacent channels. Understand that excessive frequency deviation will cause interference to adjacent channels. Well, deviation is associated with frequency modulation. So there we saw the carrier moving incrementally up in frequency and down in frequency by a small amount in sympathy with the modulating AF signal. But then we turned the gain up and the frequency, the carrier, moved further up and down than we wanted it to, and therefore it caused interference to adjacent signals or out-of-band signals. And there was a graphic to show the carrier shifting in the frequency domain too much and the interference it could cause. Recall the need to ensure that the microphone gain control, where fitted, is correctly adjusted. Well, the amount of modulation or deviation that you apply depends on that microphone gain. And if you turn it clockwise or up too much, then it will cause over-modulation. Similarly, I suppose it's analogous to an audio amplifier and a hi-fi. If you turn it up beyond where it really wants to work, it'll be outside of its dynamic range and you'll hear a distorted output. Or perhaps with a transistor radio, if you turn the audio level up too much, you will get all sorts of squawks and sounds that were not intended. So that's, if you like, analogous to turning the microphone gain up too much and causing over-deviation or over-modulation. So once again, thank you very much. Do remember that that's probably gone into it in a little bit too much detail, but I hope it's going to be helpful for you in your examinations. Thank you, and next time we will be looking at receivers.